In this presentation we are going to look at the geometric distribution, and we're also going to look at the chi-square test for the goodness of fit, which is used to just test whether or not a distribution fits the data reasonably well. Okay, so a random sample of 100 rats were each put in a maze until they were able to find the correct path out of the maze. The number of attempts required by each rat were recorded as follows. Number of attempts, and essentially what happens here is that nearly all of the rats got out within 6 attempts, and none of them needed 7 or more. That should be greater than or equal to there. But anyway, so 56 got out at the first attempt, 27 got out at the second attempt, and so on. Now, explain why the number of attempts taken by each rat might follow a geometric distribution whose probability density function is given as follows. Okay, probability of x equal to x, where capital X is the name of the variable, here the number of attempts. With the attempt actually that was the first success in this case, and 1 minus p to the power of x minus 1 times p. Now this is actually important. There's actually be multiple types. There is a different specification of the geometric distribution, which is essentially the number of failures before the first success. This is the attempt which was the first success. Okay. So the testing hypothesis that the distribution of the number of attempts needed for each rat is geometric, carefully explaining your conclusions. Okay. So anyway, let's begin. So if P is the probability of success at any given attempt, and the rat does not learn from which routes are failures, so that each result is independent of the others, then the geometric distribution explains the number of trials given to gain one success. Now this is important actually, this part. Well, P can be specified from the data, but this is a very important assumption here, that each rat does not learn which routes are failures. So if it goes in for a second time, it does not remember what it did the first time. It's starting as if it was the first attempt each time. So that is required for us to say that each result is independent of the others. Okay? If it does learn, if it does remember what happened the first time, then each trial is not independent, and then this undermines the validity of the geometric distribution. So let's just say that we're going to work on the basis that they do not remember and each is independent, each trial is independent, and so on. So what we're going to do here is estimate the value of p hat, okay, and that is equal to 1 over the mean. Okay, so what we have to do is calculate the mean number of attempts. Okay, so essentially 1 times 56 plus 2 times 27 plus 3 times 13, 4 times 3 times plus 6 times 1. Essentially it's the mean, it's the grouped mean of that table there. Okay, very straightforward calculation for 100 rats. So on average it took 1.67 attempts to get out. Okay, so that's important because that gives us our estimate for p hat, which is 1 divided by 1.67, and that is 0.5988. Okay, so what we're going to do now is calculate the table as if it was a geometric distribution using this probability. Okay, so it's a bit of number crunching here. Okay, so in the first instance, P1 is probability x equal to 1. That's straightforward enough, 0.5988. I won't use the formula in this particular instance. P2 is based on the fact that there'll be one failure before the first success. Okay, so 0.5988 times 0.4012, and that will give us a probability of 24%, 0.2402 of probability of x equal to 2, that the second attempt is the first success, and so on. So 0.5988 times 0.4012 squared. Okay, 2 failures before the first success, and that gives us a probability of 0.0964. Now, and so on and so on. So essentially, I'm not going to do them out, okay? But this is just a sort of a quick remark. You notice that after we get to probability of x equal to 4, we get into very small numbers here, okay? So the probability of x equal to 5 will be tiny, okay? It will be less than 1%. It will be about 1% actually, but essentially too small to worry about. So what we're going to do here is set up at this table here, okay? This is what we observed from the data, okay? And what we're going to do is, just for the sake of keeping our cell sizes reasonably well, or reasonably high, we're going to combine 4, 5, 6, and 7 into greater than or equal to 4, okay? So let's just go back up here, just to the raw data here. We're going to combine all of these cells into one, okay? Just because there's only 4 of them. And that makes it easier to work with without only trivial loss of information. So 56, 27, 13, and 4 or more would be 4, okay? And under the null hypothesis, we would expect, which is the geometric distribution, we would expect 59.88, okay, using these numbers for 100 rats, okay? So there's 100 rats, and the probability of a success is 0.5988. That means we would expect the probability times the sample size, the number that is the number of rats that escape on the first attempt, and so on. Okay, so we under the null hypothesis, which is the geometric distribution, we would expect 59.88 rats to escape out of 100. Okay, and remember, we can have an expected value that's not an integer. Under the null hypothesis, 24.02 rats will escape on the second attempt, 9.64 on the third attempt, and for 4 or more, we would expect 6.46 rats to require 4 or more attempts to escape. Okay, so yeah, combine greater than or equal to 4 in one class to escape very small frequencies, which is desirable, mathematically desirable. Okay. Now, so one parameter is estimated. So what we're going to use is a chi-square test here with 2 degrees of freedom for testing the geometric distribution. So what we're going to do here is calculate our test statistic to yes. And this is a very straightforward calculation, consistent with the chi-square test calculations that you would normally do. I'll just sort of remark upon the test statistic down here. It is the sum of the observed minus the expected to be squared all over the expected. Okay, and you sum them up for each cell. Okay, so that's what we're doing here. So 56 minus 59.88, square that and divide it by 59.88, and so on. So essentially what we have here is a bit of number crunching. Okay, and what we end up with is a test statistic of 2.73. Okay, so hopefully you've done the chi-square test before, so this is not new to you. Now from the tables, the chi-squared critical value is 5.99, or sometimes 5.991 if you want. And remember, that is degrees of freedom equal to 2. So there's no evidence against the null hypothesis to the geometric distribution, therefore, nor therefore against the conditions stated in A. Okay, so essentially what we're saying here is that the geometric distribution seems to be a pretty good fit, and our estimate of 0.5988 for our probability is, doesn't seem to be anything wrong with it. Okay, so that is it. That's the geometric distribution and the chi-squared